Let's crack out our LCD display. This is a 16 by 2 character Hitachi HD 44780 display. Now the HD 44780 is a very common display driver. In fact, if you've salvaged an LCD display off an old printer or something, there is a very good possibility your display may have that driver chip. The displays can take a variety of formats, 16 characters wide by 4 rows high, 40 by 2, 20 by 2, 20 by 1, etc. They also come with a variety of different colored backlights like green, amber, or blue. The datasheet is available in the download section. It's exhaustive and mostly covers the controller chips themselves because it's those chips that we're communicating with. And also those chips that drive whatever display it is you have. Now in our case, in your kit you received the 16 by 2 display. Such displays can be especially useful not just in our digital products, but also in troubleshooting or designing your circuits and programs. You'll see this firsthand as we can now get a highly informative, direct readout in plain English from your pick. Now, first thing you'll need to do is solder some wires or a header straight onto your LCD display, like I did here. This can plug straight into your breadboard. Also, unless you want to, we won't be using the D0 through D3 lines. The first thing we're going to discuss is just manually driving the display on your breadboard, and you can input the numbers either in an 8-bit or a 4-bit mode. I'll show you how to drive it in the 4-bit mode, but if you want to drive it in 8-bit mode, then you will need wires soldered to every single one of the connections. The connections from left to right are VSS, your negative supply power, VDD, your positive supply power. V0 is the contrast control for the display. You can just tie this to ground if you want, or you can put your 10K resistor from this pin to ground if you want to control the contrast. RS is one of the control lines, and it stands for Register Select. There's 2 registers you can write to. One is a control register, which receives commands or instructions for the LCD. The other is the character register, which receives the data on which character you want to display. RW is the second control line for read or write to the display. Now we'll only be writing to the display for the moment, so you can tie that to ground. E is the enable line. This is like the clock pin on digital circuits. We send a pulse on this line, it loads the register. Either the control register or the character register, whichever one you had selected by the RS line. Then you have the data lines, a 1 byte wide parallel data bus, which we're going to use as a quasi-parallel serial port, believe it or not, lines D0 through D7. Then we have A and K for anode and cathode of the backlight, which is an LED. So you need to run a 220 ohm resistor from positive to A and ground the K. This will light up the display so you can see the characters. Now what we'll do first is wire up the display to your breadboard and manually drive the display. Add a debounced push button to the E line with a pull down resistor and an RC circuit across the push button to provide sufficient debouncing. Tie RW to ground and then run jumper wires from RS and the upper 4 bits of the data lines, or all 8 bits of the data lines if you want. The schematic is in the downloads section. Now you can see what I did here. First of all, I removed one of my batteries because the display operates on a maximum of 5 volts, and I ran power up to these two buses at the top to make it simpler to connect and disconnect the wires, because the display itself blocks access to the lower buses. Now, if you're only going to use 4 bits, you can leave data lines D0 through D3 floating, just leave them disconnected. We can get away with floating wires for this experiment. When we first power up the display, we need to set up how it operates. When you first turn it on, the display is actually functioning, but the driver circuitry actually has the LCD display itself turned off. So we need to turn it on. Also, because by default it starts up in 8-bit mode, we need to tell the display we're only going to use 4-bit mode. Everything is done using the upper 4 bits of the data lines. So on page 28 of your data sheet, we can look at this chart of control signals. We can send a specific control byte down the data line, pulse the E line, and lock and load that control byte into the control register. Now, first thing we have to do is tell the display we're going to go into 4-bit mode. This saves on data lines, which, as you'll see, can be very valuable when using microcontrollers where lines are scarce. We're going to use this command right here first, function set. Now, on the page before it, you get each of those bits defined. DL is the data length. And that's one critical bit we want to use. If it is set to 1, then the display is in 8-bit mode. If it's a 0, the display is set to 4-bit mode. We want that. An unusual thing happens here in setting up for 4-bit mode. Obviously, our first 4 data lines aren't even connected to anything. So the driver chips can only see the upper 4 bits. It was designed in such a way that we can put the driver chips into 4-bit mode only using 4 bits. So as long as we have bit 5 set high, telling the display this is a function set command, and then bit 4 low, telling it the data length is 4 bits, then we've successfully set it up into 4-bit mode. So I can connect up my wires from D7, D6, and D4, making them to negative, making them a 0, and then D5 to positive. Now, nothing will happen as long as I don't pulse that E line. So I can change these wires around all over the place. We won't get any action until I hit that push button, which sends a pulse on the E line. If I may make a suggestion, you can see that the data lines on the display run least significant bit on the left to most significant on the right. This can be confusing because, everything in the text has the least significant bit on the right. However, because we're using just wires, I can crisscross all the wires when I put them up here into the bus bar. So you can see this wire is D4. This one is the most significant bit, D7. I've put them in order, least significant on the right, most significant on the left, strictly to save confusion in my poor little pea brain. Now, when we go to send our first nibble, 0, 0, 1, 0, I put this wire to positive. So now it's 0, 0, 1, 0 up here. But I also need to make sure my RW line is set to 0, connected to ground, to make sure the driver chips are in write mode. That is, we are going to write to the chips. And our RS line, our register select line, needs also to be connected to ground for a low, so that it knows that this number coming down the data lines is designated for the control register. I'm using a blue wire for my RS line. So once I've got all my lines going where they need to go, I push the push button once, sending one pulse on the E line. Now we'll have to go in blind faith here for a second because we don't actually see anything happen yet. All that has happened is we have now set up the display in 4-bit mode. All of the commands and characters are 8 bits though. So how on earth do we transmit 8 bits when we're only using 4 bits? We do it by sending the 8 bits in 2 single nibble chunks. We always send the upper nibble first, followed by the lower nibble. So we set up the upper nibble on our data lines, pulse the E line, set up the lower nibble, and pulse the E line again. The only exception is this very first function set command, which puts it into 4-bit mode. In reality, what happened is that because bit 4 was a 0, the driver chips now ignored the lower 4 bits coming in. It simply assumed that whatever came in on those lines was not valid anyway, because they're probably not even connected. However, now that we are in 4-bit mode, the driver chips are set up and expecting 2 nibble sequences coming down the data pipes. So let's now set up the display. Currently, the display is off, even though you may actually see the character blocks now. Any characters that may be there, you can't currently see. However, you'll see the byte for setting up the display. The upper nibble is all zeros, and the lower nibble has a 1 to tell it this is a display setup command, then the display on-off bit, then the underline on-off bit, then the blinking cursor on-off bit. Now, I don't know about you, I want all of those last options. So we need to send a 0000 1111. So let's hook up our wires for the first nibble. All zeros. All zeros. Hit the enable key. Then hook up our wires for all ones. And hit the enable key. Boom. The display is now active, and we have an underline on the active character, and the cursor is blinking. Now, if at this point you got nothing, disconnect the power, repower it up, and try those 3 commands again. First, send the 0010 nibble to put it into 4-bit mode, then 4 zeros, then 4 ones. Because our debounce circuit is only a stopgap measure, you may still have some bouncing going on. So you may have sent 2 or even 3 of the same nibble when you pulse the E line by pushing the button. So if after a couple attempts you don't get this blinking underline cursor, check your wiring to make sure the enable line is pulsing high. You've got the right bits in the nibble in the right, you've got the bits, in the nibble in the right order. Your RS line is tied low, and the RW line is also tied low. Stuff like that.